One of the fundamental assumptions of classical mechanics is that nature is continuous. From a macroscopic scale, this seems to be true. But now we know that matter has discrete units in the form of atoms or subatomic particles. Classical mechanics assumes that energy is continuous too. That is, there's no jump from one state of energy to another, rather, a continuous path. That is, there is no fundamental unit of energy in classical mechanics. But the same used to be assumed for matter, and now we know that matter exists in discrete quantities such as atoms or subatomic particles. So, why shouldn't energy? This is the key difference between classical mechanics and quantum mechanics. In quantum mechanics, energy exists in discrete fundamental chunks. We'll first explore how this was discovered. A black body is an ideal object that can absorb electromagnetic radiation of any frequency. Many objects behave closely to a black body, especially if it is opaque and black, which means that light won't be able to pass through, nor would light be reflected. At least, visible light won't be reflected. But a black body just needs to be good at absorbing. It can also emit light of its own at the same time. In fact, one of the key features of a black body is that every light that comes off of it is emitted on its own, not a mere reflection. Stars are a good example of a black body. Because stars don't really have a solid surface, light from the outside just dissipates within the stars. Last time, we learned that heat leads to the emission of EM radiation such as infrared light. Here's a model of the atom that physicists used back in the 19th century to explain this phenomenon. Imagine an electron on top of a spring. Because heat leads to small particles vibrating, occasionally some of these particles would disturb the electron, thus leading it to move up and down on the spring. As we learned before, light is an electromagnetic wave, which can be produced by the oscillation of an electrically charged particle, in our case, the electron. To summarize, the electron gains thermal energy and dissipates it in the form of EM energy. If an object gets hotter, it produces higher energy light, which has greater frequency. Let's take a look at some examples. The human body has a temperature of approximately 310 kelvins, which is equal to 37 degrees Celsius. We only emit infrared light. At around 800 kelvins, pretty much any object will start to glow in a dark, red, dull color. As you heat this up more, it will change into an orange color, then yellow, then light blue, slowly turning into white. From this, we can approximate the temperature of stars. An ideal black body emits light purely due to heat. So physicists Lord Rayleigh and Sir James Jeans derived a law to describe black body radiation. Here, K sub B is a fundamental constant called the Boltzmann constant, which we'll learn about later. The important thing to know about this law is that the intensity of radiation at each frequency is dependent on the temperature of the object. The law predicted that higher frequency light will be much more intense than lower frequency light, while at higher temperature, every light would become more intense. But there was one major problem with this law. The intensity of high-frequency lights increased to infinity at any temperature, an error in the law known as ultraviolet catastrophe. This meant that any object would produce infinite amount of energy, which disobeyed the law of conservation of energy quite obviously. Additionally, experimental results show that the intensity to frequency curve looks something more like this, while at higher frequencies, intensity simply decreased to zero, with the average frequency higher at higher temperatures. So, what went wrong? The greatest problem with Rayleigh-Jeans law is that it assumes every oscillator has an equal chance of being disturbed. That is, it assumes that any arbitrary value of energy can disturb the electrons because classical physics assumes that energy is continuous. This led to an issue where even the slightest bit of thermal energy would lead to every frequency of light being generated. In order to fix this, German physicist Max Planck posed a daring hypothesis. Energy is not continuous like a stream of water. Instead, energy can only be transferred to these oscillators in discrete packets of energy, like sand particles. These packets of energy are known as quanta, from which the name quantum mechanics comes from. We can see the difference between classical mechanics and quantum mechanics by looking at energy level diagrams. In classical mechanics, the oscillator can take any arbitrary value. With quantum mechanics, it can gain or lose energy only in amounts that correspond to the difference between energy levels, which is known as its quantum. This is an all or nothing event. You either have enough energy to excite the oscillator or you don't. And this is the quantum hypothesis. If high frequency oscillators have quanta of greater energy, then more thermal energy would be required to even excite it in the first place. This means that the probability of exciting high frequency oscillators diminishes, so the intensity of blackbody radiation at high frequency decreases greatly. With this concept, Planck developed a model that accurately describes blackbody radiation and solves ultraviolet catastrophe and identified an equation that describes the magnitude of quantum each oscillator takes. Epsilon is equal to h nu, where h is Planck's constant, 6.660957 times 10 to the negative 34 joule second. You can see that the constant has the unit of joule second so that it would convert frequency into energy. This relationship between energy and frequency would prove to be extraordinarily important, especially in analyzing different substances. Earlier in a discussion of the atomic theory, we encountered the cathode ray tube, and we left it with the question, why do different samples emit different colors of light? Well, we're about to answer it. Every pure sample of gaseous element or compound emits a unique series of light when it is put in flames or have electrons shot at it. We can see exactly which wavelength of light are emitted by using a spectrograph, which divides the mixture of light into component wavelengths through a prism. A detector measures the intensity at each wavelength and produces what we call an emission spectrum. You can see that for this gas, there are two thin lines of color, indicating that it only emits wavelength of these colors, these lights, in this region of the spectrum. An interesting thing to know is that gases only absorb the lights that they will emit. That is, if I lit the gas with white light, which contains all the wavelengths in the visible light spectrum, and sent the transmitted light into the spectrograph, I would see all the wavelengths in the visible light spectrum except for the two wavelengths of light seen in the emission spectrum. This is called the absorption spectrum of the gas. Because the two wavelengths were absorbed by the sample and were not allowed to transmit through, there are thin black lines instead of colors. The emission and absorption spectra of different gases are unique. Now the question was to find an explanation. In 1885, mathematician J.J. Balmer took the emission spectrum of the hydrogen atom in the visible region and found that it could be characterized by the following formula, where n is equal to 3, 4, 5, and so on and so forth. As you can see, there are 4 distinct emission lines in the visible region for the hydrogen atom: red, teal, blue, and violet. Each of these corresponds to n equals 3, n equals 4, 5, 6 in the equation, respectively. The first rough explanation of these distinct lines was from the Danish physicist Niels Bohr. Bohr postulated that each of these lines corresponds to a transition of the electrons from 2 different energy states. For instance, when the atoms absorb light, the electrons gain energy and hence move from an initial lower energy state to a final higher energy state. We call this excitation. When electrons lose energy and hence move from an initial higher energy state to a final lower energy state, the atoms emit light. We call this relaxation. The distinct frequencies of light that are seen in emission and absorption spectra are due to quantized energy states of the electrons. Electrons will only move from a unique energy level to another and either emit or absorb a quantum of light, which we call the photon. Since the energy of transition corresponds to the energy of the photon, or delta E is equal to h nu, we can describe the frequency of the photon that is absorbed with the following equation. Nu is equal to E sub f minus E sub I over h. For the frequency of the photon that is emitted, since the initial energy is greater than the final energy, the frequency of the photon is just nu is equal to E sub I minus E sub f over h. Just make sure to be careful with the signs. The idea that electrons occupy only quantized energy levels explained the ultraviolet catastrophe and emission and absorption spectra of the atoms, none of which classical mechanics could explain. Another concept classical mechanics couldn't explain was the structure of the atom. The last structure of the atom we learned was the Rutherford planetary model, where the electron orbits around a dense nucleus, much like a planet orbiting around the sun. In this model, the force that connects the electron with the nucleus is the electrostatic force that attracts them. Now, the electron orbits around the nucleus and therefore it accelerates. Any charged particle that accelerates will produce electromagnetic radiation, losing energy and moving closer to the nucleus. Eventually, it will spiral all the way down to the nucleus. To put it simply, what made the electron just stay in an orbit, as Rutherford described it? Why wouldn't it just fall all the way down like an apple falling down on the ground? First, Bohr stated that electrons existed only in quantized energy states, described by the extremely popular model of the atom known as the Bohr model. As you can see, the Bohr model of the atom is very similar to the Rutherford model, except that it has multiple orbits the electron can fit in. In this atom, the innermost orbit is the lowest energy electrons can occupy, and there are other higher energy orbits that electrons can occupy. They cannot exist in between. By quantizing the energy states of electrons, Bohr avoided the paradox that classical mechanics presents in the Rutherford model of the atom. Now, for the second half of this lecture, I will walk you through how Bohr's assumption translated to mathematics and how it explained frequencies of hydrogen emission and absorption spectra. The derivation itself is well outside the scope of AP chemistry and is slightly, honestly, pretty rigorous, but understanding the thought process helps you appreciate the logic behind the final equation that we will come up with. You may skip to the part where I write this equation, but otherwise, pay close attention. The development of every mathematical model begins with the simplest example. In the case of Bohr, he chose to describe single electron atoms because they only have two charged particles, an electron and a nucleus. In the hydrogen atom, the nucleus has plus 1 charge. In a helium plus ion, the nucleus has plus 2 charge. In a lithium 2 plus ion, the nucleus has plus 3 charge. The charges of the nuclei differ, but the general structure is the same, an electron and a dense nucleus. Bohr's theory started from Rutherford's planetary model, which assumed that a single electron of charge minus e and mass m sub e moves with speed v in a circular orbit of radius r, about a fixed dense nucleus of charge plus zt. Since the electron is moving and an electrostatic force exists between the electron and the nucleus, the total energy of the atom can be described by the sum of the kinetic energy of the electron and the electrostatic energy of the atom. Along with this equation that describes the total energy of the atom, Bohr also used an equation that relates force and acceleration of the electron. There is an electrostatic force acting on the electron, and the electron accelerates so that it moves in a uniform circular motion. A particle moving in a uniform circular motion has acceleration of a is equal to v squared over r. And since force equals to mass times acceleration, we can equate electrostatic force with this acceleration multiplied by the mass of the electron. So far, Bohr only used concepts from classical physics, which he already knew wouldn't be enough to describe his model of the atom. In the third and final equation, Bohr employed quantum mechanics, but it was also a complete assumption. That is, it had no experimental basis yet. It was nothing more than just a sophisticated guesswork. Since he had to quantize the orbits of the electrons, he decided to quantize a quantity known as the angular momentum, L, which describes the angular motion about an axis. While linear momentum is the product of mass and velocity, angular momentum is the product of mass, velocity, and the radius of the particle from the axis of rotation. In this case, m sub e vr. Bohr postulated that the angular momentum of the electron is quantized in integral multiples of h over 2 pi, where h is Planck's constant. This is the final equation Bohr established for his theory, where n is equal to 1, 2, 3, and other positive integers. To recap, equation 1 describes the total energy of the atom. Equation 2 describes the force and the acceleration of the electron. Equation 3 describes the quantization of angular momentum in the electron. Now, Bohr had all the equations he needed in order to find out the properties of the discrete orbits of the electrons. The first property he could find was the radius of each orbit. In equation 2, there are two unknowns, v and r. Using equation 3, he described the velocity of the electron in terms of the radius of the orbit. He substituted the velocity in equation 2 with this expression, obtaining the following equation. You can see that many of these variables and constants can be cancelled out. Here, everything is a constant except for n and z, which are positive integers. Therefore, we can describe the radius of the orbits in a single electron atom of atomic number z by isolating the radius r. And again, since everything is a constant except for n and z, we can express the constants with a new single constant, a naught, which has the value of 5.29 times 10 to the negative 11 meters, or 0.529 angstrom. This is the Bohr radius, a convenient unit of length in atomic physics. As you can see, increasing the charge of the nucleus decreases the radius of the orbits quite greatly. For example, a single electron helium ion would be smaller, twice as smaller as a hydrogen atom. This makes intuitive sense since stronger nuclear charge means stronger electrostatic attraction, pulling the electron closer to the nucleus. With increasing n, the radius of the orbit increases dramatically. Since the electron experiences smaller electrostatic attraction due to greater distance, it will have higher energy. In fact, Bohr found an equation that describes the energy state of each orbit in his model. By taking the expression of r sub n and substituting it into equation 3, he found the speed v sub n of the electron in the orbit. Taking the expressions for v sub n and r sub n and substituting them into equation 1, Bohr found the energy level of each orbit. This is the equation for the energy of an orbit in a single electron atom. As you can see, the energies are negative since we're discussing energy due to positively charged nucleus and a negatively charged electron. Like the radius, there are many constants in this equation. We can simplify this equation by substituting the constants with the Rydberg unit, 1 Rydberg, which is equal to 2.18 times 10 to the negative 18 joules. Then the equation becomes E sub n is equal to minus z squared over n squared Rydberg. Let's examine the first 5 energy levels of orbits in the hydrogen atom using this equation. Since z is equal to 1 for hydrogen, and n will equal to 1, 2, 3, 4, and 5, we see that the possible energy levels are simply E sub 1 is equal to minus 1 Rydberg, minus 1/4 Rydberg, minus 1/9 Rydberg, minus 1/16 Rydberg, and minus 1/25 Rydberg. It's important to note that these energies all have negative values, so with increasing n, the energy increases. This is the quantized energy levels that Bohr described for the hydrogen atom, the most important of which is the energy at n equals 1, the lowest possible energy level an electron can occupy. We call this the ground state. Any state above it is called an excited state of the electron. The most important takeaway so far is that with increasing n, the radius and energy level increase. We can visualize this through this figure. You need to invest energy in order to push the electron upwards to each ring, pushing it further away from the influence of the nucleus. Do note, however, that the electron can only exist on the ring, not in between, like this figure suggests. The magnitude of energy associated with the transition between energy levels can be described through this equation. Since the change in energy is equal to the final energy minus the initial energy, substituting the equation in, we can find that for single electron atoms, this equation is true. For the hydrogen atom, Z is equal to 1, so this equation will be true. When n sub I is equal to 1 and n sub f is equal to infinity, an electron is being elevated from the ground state all the way to the state that would get it to be infinitely far away from the nucleus's influence. That is, we're moving the electron entirely away from the atom. If we substitute these values into the equation, we find that it simply reduces down to delta E is equal to 1 Rydberg, which is equal to 2.18 times 10 to the negative 18 joules. This is the ionization energy of the hydrogen atom, the minimum energy required to remove an electron from an atom, making a singly charged cation. Multiplying this extraordinarily small value by Avogadro's number gives the ionization energy, i.e., per moles of atoms for hydrogen. This value is extremely close to the measured ionization energy for hydrogen, 1312 kilojoules per mole. We close this lecture by relating the transition equation with the Balmer series. Examining the two equations, we already see similarities. They both involve differences in the reciprocals of squared integers. How do we relate transition energy with frequencies in the Balmer series? Well, it's simple. We know the equation for energy transitions in single electron atoms, and we know the formula that relates energy with frequency. Combining those two, we get the following equation. Isolating for the frequency, we get this equation. Since H is equal to 6.66 times 10 to the negative 34 joules second, the joules cancel out, leaving a value with the unit of frequency. This final equation is known as the Rydberg equation, an equation that relates the frequency of emitted or absorbed light with energy transition of the electron. From this equation, we can finally learn why different elements emitted different colors of light in the cathode ray tube. Each element has a different atomic number. Thus, the frequencies of emitted light will be unique for each element. For the hydrogen atom, Z is equal to 1, so if we wanted to find the inverse of the wavelength of this light, we simply use the fact that wavelength times frequency equals the speed of light, which is a constant. In this equation, R sub h is equal to 1.097 times 10 to the 7th power per meter. This is the Rydberg constant for the hydrogen atom, the inverse of the maximum wavelength of light that can ionize the hydrogen atom. With this in mind, we can finally see how exactly the Rydberg equation relates to the Balmer equation. The Balmer equation is simply the Rydberg equation for the hydrogen atom with n sub I equals 2. That is, what frequencies of light are absorbed to excite the electron from n equals 2. Conversely, what frequencies of light are emitted when the electron relaxes to n equals 2. In the emission Balmer series, the red line corresponds to relaxation from n equals 3 to n equals 2. The teal line corresponds to relaxation from n equals 4 to n equals 2. Blue is relaxation from n equals 5 to n equals 2, and violet from n equals 6 to n equals 2. Further experimentation showed other series of light that corresponded to other transitions for the hydrogen atom. For instance, the Lyman series, which is in the ultraviolet region. The Lyman series shows the frequencies for relaxation to n equals 1. Since the electron experiences a greater energy transition, the emitted light will have greater energy and therefore greater frequency. On the other hand, the past-gen theory shows the frequencies for relaxation to n equals 3, and it's in the infrared region. We can extend this idea for different quantized electron states to other elements. Different elements will have different allowed energies for their electrons, so the frequencies of light that can be released or absorbed will be unique for each element. This is the reason why we can identify an element through a flame test. When you put a metallic element in a flame, the heat will excite the electrons. When the electrons relax, they will release light of the same energy, and the cycle of excitation and relaxation continues. Lithium is red, sodium is orange, copper is green, and potassium is pink. This is actually how we determine the colors of fireworks. The Bohr theory predicted the frequencies extremely accurately for the hydrogen atom, proving itself to be a massive success. However, it is definitely not perfect. It has two huge problems. The first is that the Bohr theory can only be applied to single electron atoms. If it had two or more electrons, it would have to take into account multiple forces, and that would be too complex. The other problem is that Bohr combined concepts from classical mechanics and quantum mechanics in order to reach its conclusion. Thus, even though it predicts experimental results for the hydrogen atom very well, it is fundamentally flawed and requires many assumptions, most notably the quantization of angular momentum. In our next lecture, we will see that the classical idea of electrons orbiting around the nucleus is, in fact, completely wrong. We will transition from classical mechanics to quantum mechanics entirely, understanding the modern and latest model of the atom.